All right. So in that last example, on part 1, we looked at how to approximate the area between a curve and the x-axis, which again, remember, we just call that area under a curve. By taking the interval 0, 1 that we wanted to find the area over, and cutting it up into 4 little sub-intervals, and then constructing rectangles over those, where the height of the rectangle was determined by either taking the left or the right endpoint of your subinterval, plugging it into the function, and that gave you the height of that rectangle. We saw in that last example as well that our area can be under-approximated if we use left endpoints or over-approximated if we use right endpoints. And so the area that we are actually looking for was somewhere in between the 2 estimates that we found. Now, I chose 4 subintervals to break the interval 0, 1 into, and there was no real reason to choose 4. I could have cut that into any number of subintervals that I wanted to. And so what if instead I cut it into, say, 8 subintervals? Well, in that case, I would have something that looks like this. Notice I have left endpoints that I'm using for the heights of my rectangles here, using right endpoints for this other approximation here. I'm still seeing an underestimate on this side and an overestimate on this side. But if you look at the gaps here and here and here and here, those gaps are noticeably smaller than the gaps I saw here. There's a lot more empty space here in this underestimate than there is here. So I would expect this to be a better approximation for the true area under that curve than in the previous example where I used only 4 subintervals. Something similar happens here. I'm overestimating the area because we have this extra little bit of each rectangle that goes over the curve, but the amount of excess that I get in each rectangle is noticeably smaller than the amount of excess that I got in this example. So my expectation is that both of these approximations will be better or closer to the true area that I'm looking for than when I only used 4 subintervals. We're not going to go through the setup and the computation for it, but if you were to compute these areas with these 8 subintervals, either using left or right endpoints, we would have gotten these values. I'm using L8 for left endpoint with 8 subintervals, R8 for right endpoint with right endpoints with 8 subintervals. So this would tell me that the area is somewhere between 0.273435 and 0.398435. That is a closer or a tighter approximation than what we got here. That was a wider interval that I found. So with using more rectangles, more subintervals, it appears that I'm getting a better and better approximation. So now you can naturally ask, well, is there anything special about the number 8 for the number of subintervals? And again, no. All that mattered is that we allowed ourselves to cut the interval 0, 1 into more subintervals than our previous example. So we can continue doing that. I can cut this into 10 subintervals, or 100 or 1,000 subintervals. And I would expect that the more subintervals I cut the interval 0, 1 into, giving me more rectangles, the better my approximation for that area should be. So down here I have a table of left and right endpoint approximations for the area that we're looking for a variety of different numbers of subintervals that we cut the interval 0, 1 into. 10 subintervals, 20, 30, 50, 100, 1,000. And look at what's happening to the approximations. My left endpoint, which we know is giving us under approximations every single time, is getting bigger and bigger. It seems to be kind of approaching something here. And then the right endpoint method, which is giving me overestimates, those overestimates are getting smaller and smaller. So in both cases, I'm expecting this to be approaching the true area that I'm looking for. And look at how close these numbers are right here. 0.332, 8335. 0.333, 8335. They only differ by like 1/1000th. So my area is somewhere in between there, and I might even be able to guess what it is at that point. The point is, and I'll show you in this picture on the next page as well so you can visualize it. Once again, We can approximate the area between a curve and the x-axis over some interval by chopping that interval up into subintervals and constructing rectangles, either using right endpoints, left endpoints, or we'll talk about there, you can really choose any point in each subinterval to do that. Those give you estimates, but those estimates can be improved by increasing the number of rectangles you chop your interval into, or number of subintervals you chop your interval into. And you can see in these pictures how the area of those rectangles seems to be conforming more and more to the actual area of that region. Okay, now that might be hinting at how to make this approximation exact, but we're not going to get to that quite yet. That'll be later in this section. I just wanted you to keep in mind this pattern that we're noticing here. Okay, so now it's time to kind of formalize a little bit of this. So like I was saying just a second ago, we keep using left or right endpoints to determine the heights of those rectangles that we're using for our approximation. But there is no requirement that you're choosing exactly the left or the right endpoint to do that. You can actually, once you've taken your interval and chopped it up into subintervals, you can pick any point in any of those subintervals that you want to then plug into your function to give you the height of that rectangle. We call that point a sample point. And the notation for it, if we're talking about the ith subinterval, so I is just some integer. If it's 2, for example, I'd say the second, subinterval or something like that. We choose a sample point in there, which we call xi star. It's just some number between xi minus 1 and xi, the endpoints of that interval. It could also equal either one of those endpoints, in which case we're looking at a left endpoint or a right endpoint method. But those are called sample points. So now that we've mentioned that, we can talk about we can put a name to this thing that we've been doing. So suppose you have some function f defined on an interval AB, and you've divided that interval up into n subintervals. So instead of 4 or 8 or 10 or 100 or 1,000, we're just going to be general and call it n. We're going to let delta x equal b minus a over n. Now remember what that is. Delta x represents, I'm going to find that page where I did this. Delta x represents the width of any one of these subintervals. And remember how here we said that it's just the difference between the endpoints of the larger interval divided by however many subintervals you want to cut it into. So in this case, it looked like 1 minus 0 over 4. But in this general case, it's b minus a over n. That would be the width of any one of those subintervals. And as we mentioned up here, xi star is a sample point, and it's just any x value that comes from the ith subinterval. So the subscript here denotes which subinterval it belongs to. Okay? Then we define this thing called a Riemann sum, and it's equal to, here's where that summation notation is making an appearance. It's the sum from I equals 1 to n of f of xi star times delta x, which, if you expand that out long ways, looks like this. Think about what this is. Delta x is the base of any one of those rectangles. F of xi star is the height of the ith rectangle. So what we're doing is every time we plug a number from 1 to n into the subscript here, we're finding the height of the ith rectangle, multiplying it to the base. Now what we get is the area of that ith rectangle. And since we're adding up the areas of all of those rectangles, that is the approximation for the area that we're looking for. So this notation is just mathematical notation for what we've been doing this whole time, adding up areas of rectangles. Okay? All right. The name Riemann is capitalized because it's named after a mathematician. One of the most important mathematicians who ever lived, Bernard Riemann, was very prolific mathematician. He did a lot for the subject back in the 19th century. We don't need to make a history lesson out of this, but just in case you're wondering why that's capitalized and why we call it what we do, it's one of many things that are named after that guy. All right, that's enough on that. So now here's what I want to do. I want to estimate the area under the curve y equals 1/4 x squared plus 2 on the interval from -2 to 10 using a Riemann sum with 6 subintervals where each sample point is the midpoint of a subinterval. We call this a midpoint Riemann sum. So up until this point, we've been using left endpoints or right endpoints, and this time I want to use a midpoint. Now, you don't have to sketch the curve and draw the rectangles in order to do this. I am going to do it here because I want to show you what happens when you use midpoints. But in future examples, I'm not going to sketch the curve every single time. So let's take a look at this. I hope I gave myself enough space there. All right, we're going from -2 to 10. So let's put -2 like there. We'll put 10 right here, okay? This function, I don't need to make this like super exact in order to do this, so I'm just going to get a general idea of what this looks like. But it's a quadratic, so that means that it's going to look like a parabola. And it's x squared times 1/4. That makes the parabola wider when I multiply it by a fraction. Plus 2, that shifts the whole thing up 2 units. So it's going to go up here to 2. And the parabola is going to look something like this. This is not super accurate, but it's going to serve the purpose that I want it to serve here. So roughly like that, right? Okay, we want to use a total of 6 subintervals. First thing I'm going to do is figure out what delta x is. So remember, delta x is b minus a over n, where n is the number of subintervals we're using. B minus a in this case looks like 10 minus -2, and we're dividing that by 6, the number of subintervals. 10 minus -2 is the same as 10 plus 2. So this is 12 over 6, or 2. Okay, so that means each subinterval is going to have a width of 2. That means I can start at this left endpoint here and just count by 2s to get all of the endpoints of the remaining subintervals. So -2 plus 2 is 0. I don't need to mark that. Plus 2 again, 4 plus 2 again, 6 plus 2 again, 8. Okay, it's not very well drawn. You can see that it's kind of gets squished over here. Don't worry too much about that. Now I'm going to construct rectangles, but I'm going to use not the left or the right endpoint of any one of these subintervals, but the midpoint specifically. So to find the midpoint of an interval, you can just add up its left and right endpoints, then divide by 2. You're finding an average. Or, in this case, it's pretty easy to eyeball it and see what they are. -1 is in the middle of that subinterval. +1 is in the middle there. 3 would be in the middle there. 5 is in the middle there. Then 7. Then 9. Okay? So now what I'm doing, I'm taking these midpoints here, I'm plugging them into my function to get me up to a point, and then that point determines the height of this rectangle. Okay, so plug that in. That's going to give me the height of this rectangle here. So we've got 2 rectangles. Plug this in. That gets me the height of this rectangle. Plug that midpoint in. That gets me the height of this rectangle. Plug this midpoint in. Got the height of that one, so I can kind of sketch that rectangle. And then this guy, plug that in. Gets me the height of this. Okay. Before we go any further, I want to talk about why it's really nice to use midpoints as opposed to a left or a right endpoint. So when we use left and right endpoints, we saw that we were pretty consistently underestimating or overestimating by a fairly decent amount. We have a lot of gaps or excess in our approximations. Midpoints help to balance that. Pick any one of these 6 rectangles. For example, this one right here. I have some excess area right there that goes above the curve, but then I also have a gap right here. So the excess and the gap help to cancel each other a little bit, which means the area of this rectangle is going to be fairly close to the area of just this little region over the subinterval, which means I'm going to be minimizing the amount of error I introduce into this approximation. So that's kind of why you might choose midpoints over a left or a right endpoint. But now that we have seen that in this picture, for future examples, I'm not going to like sketch this curve and sketch these rectangles anymore, because you technically don't need to if you understand the technique. At this point, let's go to the definition for our Riemann sum. So you don't have to use the summation notation, but for the sake of practice, I'm going to do it. We're going from I equals 1 to 6, because that's how many subintervals I'm using, right? From 1 to 6 of f of xi star delta x, and xi star represents these sample points. In this case, it was the midpoints that we plugged in. So maybe just for my own reference, I might write x1 star equals this first midpoint, -1. x2 star equals that second midpoint, 1. And then I don't need to write all of them, but this is just so I can see the pattern. Let's go ... out to x6 star, which was this last midpoint here. That's 9, okay? Furthermore, what is f of x? Well, this is f of x. It's the function that gives me the curve in the first place. So this is the thing that these midpoints are being plugged into in the course, over the course of this summation. So now let's actually do this. F of xi star is equal to what? Well, I'm plugging -1 into this function. So that's 1/4 times -1 squared, right? And then I need to multiply that by this delta x. The delta x is 2. I'm missing something important. It's not just 1/4 x squared. It's 1/4 x squared plus 2. Okay. I have to multiply that entire thing by 2. However, I'm also going to be multiplying all of the remaining terms in this sum by 2, since delta x is equal to 2 for all of these subintervals. So one thing you can do to save yourself a little bit of time is to preemptively factor that delta x, or that 2, out. Saves a little bit of time, okay? So here is f of x1 star when I plug that into my function. -1 gets plugged in, it would give me this. And then I don't need parentheses, but I'm going to do this just so you can kind of see the separation of things. Plus 1/4 times x2 star, that's 1 squared, plus 2. So I'm counting my way up, right? Counting my way up until I get to this last f6 star, which is 9, plus 1/4 times 3 was the next midpoint. I can use my picture for that, squared plus 2. I'm not going to have enough space, so I'm going to write the rest down here, plus 1/4 times 5 squared plus 2, plus 1/4 times 7 squared plus 2, plus 1/4 times 9 squared plus 2. I was using square brackets. Let's keep it to square brackets. Okay. At this point, this could go into a calculator. There is so much going on here. It'll take you a while to type all of that in. You can use some simplification, though. If you notice, the fact that we're repeating something that looks very similar every step of the way, you can do a little bit of time-saving stuff here. So, for example, that 2 is still on the outside. You can drop all of these sets of parentheses. There's not any purpose that they're serving other than to show us that each one of these little groupings came from, a term in this sum. But if you drop all of those, you can see that you're adding 2 up a total of 6 times. So that's just 2 times 6, which is 12. I'll write that in a second. In addition, if you group up all of these terms, 1/4 times this squared, 1/4 times that squared, 1/4 times this squared, you can factor a 1/4 out of all of that. So if I did -1 squared, that would be 1 plus 1 squared, that's 1. 3 squared is 9. 5 squared is 25. 7 squared is 49. 9 squared is 81. Then this accounts for all of these terms here. And then, like we said, you're adding 2 up 6 times, so that's just plus 12. Notice I still haven't gotten an answer, but I can do a lot of very quick algebra to simplify this, so that when I do plug it into a calculator, or if I do want to work it out by hand, it's much, much easier. Okay, it's good to know how to do that kind of stuff. This works out to 120. Okay. Is that the exact area? No, not necessarily. It's an approximation. But from the picture, which I know is not a perfectly accurate picture, we can trust that because we chose midpoints, this is a decent approximation. Okay? All right. I'm going to do this next example in part 3.